Is the solid reality around us nothing but an elaborate illusion? This is the startling claim of the holographic principle, a theory at the forefront of physics. It proposes that our entire universe, with all its stars and galaxies, might be a projection from a hidden, two-dimensional surface. Your entire three-dimensional experience could be encoded on a distant cosmic boundary, like a hologram. By the end of this journey, you will understand the profound evidence suggesting that space and time are not fundamental. We will uncover why black holes seem to erase information and how the fabric of spacetime might be woven from quantum entanglement. Are you ready to question everything you think is real? The roots of this radical idea lie in a deep conflict between our two most successful theories of reality. For decades, general relativity and quantum mechanics have been at war, and their fiercest battlefield is the edge of a black hole. It was a young graduate student named Jacob Bekenstein who, in the 1970s, made a startling calculation. He was studying the thermodynamics of these cosmic traps and realized something profound. A black hole must have entropy. Now, entropy is a measure of disorder, but more fundamentally, it is a count of the hidden information within a system. Think of a messy room. The more cluttered it is, the more ways its contents could be arranged, and the higher its entropy. Bekenstein found that a black hole's entropy is not proportional to the volume of its vast, dark interior, as you might expect. Instead, it is precisely tied to the surface area of its event horizon, that point of no return. This was bizarre. In our everyday world, the amount of information something can hold always scales with its volume. A bigger hard drive stores more data. A larger book contains more words, but here was a cosmic object, the most information-dense thing conceivable, declaring that its entire informational content was painted onto its two-dimensional surface. This strange result was just the beginning. Then Stephen Hawking entered the fray. He demonstrated that black holes are not completely black. Due to weird quantum effects near the event horizon, they slowly leak radiation. They evaporate, fading away over astronomical eons. This discovery, Hawking radiation, created a terrifying paradox. If a black hole evaporates entirely, what happens to all the information about the stars, gas, and atoms that fell in? Quantum mechanics has a sacred rule. Information cannot be destroyed. It can be scrambled, but it must, in principle, be recoverable. Hawking's work suggested that information was being permanently erased from the universe, a violation of the fundamental laws of physics. This was the black hole information paradox, a crisis that hinted our understanding of spacetime was profoundly incomplete. The solution, waiting in the wings, was a concept so bold it would reframe the cosmos. The stage was set for the holographic principle to make its grand entrance. This paradox seemed to shatter the foundations of physics, demanding a solution as radical as the problem itself. In the 1990s, two brilliant minds, Gerard T. Hooft and Leonard Susskind, took Bekenstein's strange calculation and ran with it. They dared to ask a question that flipped reality on its head. What if the universe was not storing information the way we think it does? What if, like a hologram, our three-dimensional world is actually a projection from a two-dimensional surface? A hologram, like the kind you might see on a credit card, is a flat surface that somehow contains all the information needed to create a stunning three-dimensional image. T. Hooft and Susskind proposed that reality itself might work the same way. They theorized that the entire description of a volume of space, every particle, every force, every event happening within it, could be perfectly encoded on its outer boundary. For a black hole, this boundary is the event horizon. Susskind had a brilliant insight that resolved the information paradox. He argued that when something falls into a black hole, the information it carries is not lost into the mysterious singularity. Instead, like a cosmic fingerprint, that information is smeared and stored on the two-dimensional surface of the event horizon. Then, as the black hole evaporates through Hawking radiation, that information is slowly and carefully released back into the universe. The information was never destroyed, it was just translated from a three-dimensional form into a two-dimensional one and back again. This was the holographic principle, a concept so profound it redefined the nature of reality. If it was true for black holes, the most extreme objects in the cosmos, why not for the entire universe? The principle suggests that everything you see, feel, and experience, the vast three-dimensional tapestry of stars, planets, and life itself, could be nothing more than a magnificent projection. All the information that makes up our reality might be written on a distant, two-dimensional surface at the edge of the cosmos, a cosmic film containing the ultimate movie of existence. This idea forces us to confront a staggering possibility that our perception of a solid, three-dimensional world is a beautiful and convincing illusion. But how could such an outrageous idea possibly be true? To find out, we must descend into a theoretical battleground where the nature of space and time is forged. This abstract idea found its most powerful expression in a mathematical discovery that shook the foundations of theoretical physics. In 1997, a young physicist named Juan Maldaisner unveiled a concrete framework that gave the holographic principle a precise, calculable form. His work is known as the AD/CFT Correspondence, and it is essentially a cosmic dictionary. It establishes a perfect duality, a complete equivalence between two seemingly different worlds. On one side of this duality is a universe described by a version of string theory. This universe, called anti-de Sitter space, is a strange, saddle-shaped cosmos with a negative curvature that causes it to bend inward on itself. Crucially, this is a universe that contains gravity with three spatial dimensions plus time. On the other side of the duality is a conformal field theory, a type of quantum theory that lives on the two-dimensional boundary enclosing that strange, warped universe. This boundary theory has no gravity at all. It describes particles and forces interacting on a flat surface, much like the theories physicists use to describe subatomic particles in our own world. Maldaisner's stunning insight was that these two theories are not just similar, they are exactly the same thing, described in two different languages. Every single event, every particle collision, every gravitational whirlpool within the three-dimensional bulk of that warped space has a perfect, one-to-one translation into the interactions of quantum fields on the two-dimensional boundary. Think of it like a movie and its script. The three-dimensional universe with gravity is the spectacular film you watch on a screen, full of action and depth. The two-dimensional quantum theory is the complete script, every line of dialogue and stage direction written on pages of paper. The script contains all the information needed to generate the entire movie. In the same way, the flat quantum theory contains all the information necessary to build the entire universe with gravity. This correspondence is more than a philosophical curiosity, it is a powerful tool. Physicists can now take incredibly difficult problems involving gravity and black holes in the three-dimensional world and translate them, using the dictionary, into much more manageable problems involving quantum particles on the two-dimensional surface. Problems that were once considered impossible to solve have suddenly become tractable. This mathematical reality forces a profound question upon us. If a universe with gravity can be completely encoded on a lower dimensional boundary without gravity, What does that say about our own cosmos? We do not live in an anti-de Sitter space. Our universe is expanding in a different way. Yet, the sheer success of this holographic correspondence suggests that the principle might be a fundamental feature of reality itself. It invites us to consider a staggering possibility that our own four-dimensional spacetime, with all its galaxies and stars, might be a holographic projection from a vast, two-dimensional surface at the edge of everything we know. If our universe is a hologram, then what is it actually made of? The answer may not be matter or energy, but something more fundamental: information. Think of a digital photograph on your screen. It looks like a smooth, continuous image, but if you zoom in far enough, you see it is actually composed of tiny, individual pixels, each one holding a specific piece of data about color and brightness. The holographic principle suggests that reality itself operates in a similar way. At the tiniest possible scale, the fabric of space may not be smooth and continuous. Instead, it could be pixelated, woven from unimaginably small bits of information. This fundamental scale is known as the Planck length, a distance so minuscule that it makes an atom look like an entire galaxy in comparison. At this level, the universe might be storing its most basic data, but here is the crucial twist from the holographic principle. This information is not stored in the volume of space, like data scattered throughout a hard drive. Instead, it is all encoded on a distant two-dimensional surface, the cosmic boundary. Our three-dimensional reality, with its rich tapestry of stars, planets, and people, is then a projected image, an emergent phenomenon that arises from the complex processing of that underlying data. This leads to a staggering conclusion. Spacetime itself may not be a fundamental stage upon which the universe plays out. The force of gravity, which shapes the cosmos, may not be a fundamental force at all. They could both be emergent properties, collective behaviors that arise from the intricate interactions of countless bits of information on the boundary, much like the temperature of a gas emerges from the frantic motion of its individual molecules. You do not feel the impact of each single molecule, you feel their collective behavior as warmth. In the same way, we do not perceive the individual bits of cosmic code, we perceive their collective organization as the force of gravity and the geometry of spacetime. This reframes our entire existence. We are not solid beings moving through a solid world. We are complex, dynamic patterns in a vast, flowing stream of information. Our thoughts, our planet, the most distant galaxy, all could be manifestations of a cosmic computation happening on a two-dimensional screen at the edge of everything. This is not just philosophy, it is a physical theory that makes a bold, testable prediction. If space is pixelated at the Planck scale, then there should be a fundamental graininess to reality, a subtle blurring of the sharpest images the universe can provide. The quest is now on to find this cosmic static, the faint noise in the data of reality that would reveal the holographic illusion for what it is. Isaac Newton envisioned the universe as a grand, predictable stage. In his classical view, space and time were absolute and unchanging, a smooth and continuous backdrop against which matter moved with clockwork precision. Objects interacted through forces that acted locally, touching or pushing each other in a well-defined neighborhood. This framework was immensely powerful, describing everything from a falling apple to the orbits of planets. Then Albert Einstein arrived and revolutionized this stage itself. He wove space and time together into a single, dynamic fabric called spacetime, a manifold that could curve and warp in the presence of mass and energy. Yet, even in Einstein's relativity, this fabric remained fundamentally smooth and continuous. It was a classical reality, just a far more flexible and intricate one. The holographic principle shatters this entire conception. It tells us this smooth, continuous spacetime is not the foundation of reality, but an emergent illusion. The universe is not a perfectly woven fabric, it is pixelated. At the tiniest possible scale, the Planck length, reality possesses a fundamental graininess, as if the cosmic movie is being projected from a finite resolution screen. This is not a minor tweak to our understanding, it is a paradigm shift as profound as the quantum revolution itself. The most staggering casualty of this new view is the principle of locality, the very idea that objects are only influenced by their immediate surroundings. In a holographic universe, what happens here might not be determined by the space right next to you. Instead, the true interactions, the real processing of information, could be happening on a distant two-dimensional boundary. The apparent local connections we see in our three-dimensional world could be a projected shadow of deeper, non-local links encoded far away. Two particles entangled in our space, instantly influencing each other across vast distances, might not be communicating faster than light through the void. Their connection could be a direct consequence of their information being processed right next to each other on that ultimate cosmic hard drive. This radical departure from locality is not just philosophical speculation, it is a concrete, physical claim with potential experimental consequences. This strange departure from locality points directly to the weirdest phenomenon in all of physics, quantum entanglement. We have long known that two particles can become linked or entangled in such a way that measuring the state of one instantly determines the state of the other, no matter how far apart they are. Einstein famously called this spooky action at a distance, an unsettling idea that seemed to violate the cosmic speed limit set by light. For decades, entanglement was seen as a bizarre but marginal feature of the quantum world, a curiosity that did not affect the larger scales of reality. The holographic principle turns this view completely upside down. It suggests that entanglement is not just a quirk, it is the very glue that holds the fabric of spacetime together. In the holographic framework, the vast network of entanglement between the quantum bits on the two-dimensional boundary is what actually builds the geometry of the three-dimensional world we inhabit. Think of it like this. Imagine the boundary of the universe is a vast sheet covered in a billion tiny lights. Each light represents a fundamental unit of information. Now, imagine connecting these lights with threads. Each thread represents a quantum entanglement between two bits. If you only have a few threads, the lights are only loosely connected, and the structure they project is weak and poorly defined. But if you weave a dense, intricate web of threads connecting nearly every light to many others, this complex network of connections projects a rich, robust, three-dimensional space. More entanglement literally builds more space-time. The very distance between 2 points in our universe might be a measure of how deeply entangled the underlying boundary information is. This transforms our understanding of reality at the most fundamental level. The force of gravity, the curvature of space, the very fact that you can move from one place to another, all of it may emerge from this underlying quantum tapestry of spooky connections. Entanglement is no longer a sideshow, it is the main event, the fundamental thread stitching the cosmos into a coherent whole. This profound link between information and geometry begs a critical question. If this is how our universe is built, how can we possibly find evidence for it from within the projected world we call home? The search for this cosmic static has already begun, pushing the limits of human precision. At the Fermi National Accelerator Laboratory, an ambitious experiment called the Holometer is listening for the faintest whisper of reality's digital code. This device is not a traditional telescope, it is a laser interferometer, an instrument of incredible sensitivity. It works by splitting a laser beam and sending the two halves down perpendicular arms several stories long. The beams bounce off mirrors and return, recombining to form an interference pattern. In a perfectly smooth and continuous space-time, that pattern would be stable and predictable. But if space itself is pixelated at the Planck scale, then the very positions of the mirrors would be subject to a fundamental, irreducible jitter, a kind of quantum fuzziness known as holographic noise. The holometer is designed to detect this minuscule shudder, a vibration in the fabric of reality so tiny it would take thousands of years for it to move an object by the width of a single atom. Imagine trying to measure the roughness of a mirror by using a wavelength of light. If the mirror were perfectly smooth, the reflection would be pristine. But if the surface had a fine, sandpaper-like grain, the light would scatter in a subtle, telltale way. The holometer is looking for the equivalent of that scatter in spacetime itself. The initial results from this pioneering instrument have not yet provided a definitive discovery, but they have placed new, stringent limits on the possible intensity of this holographic noise. The hunt is far from over. Newer, even more sensitive experiments are being planned, each one a more powerful microphone pressed against the cosmos, listening for the faint hum of its underlying code. This is the point where abstract mathematics and mind-bending theory collide with the tangible, measurable world. The ultimate validation of the holographic principle will not come from a blackboard calculation alone, but from a signal, a tiny tremor in a lab, a piece of data that reveals the pixelated screen upon which our magnificent reality is projected. Finding that signal would be one of the greatest scientific discoveries in history, fundamentally rewriting our story of what the universe is and what we are within it. This radical idea does not just apply to theoretical warped spaces. It forces us to look at our own universe with new eyes. The cosmos we inhabit is expanding at an accelerating rate, driven by a mysterious force known as dark energy. For decades, physicists have searched for the source of this energy, often invoking exotic new particles or unseen fields. But the holographic principle offers a breathtakingly different solution. What if dark energy is not a substance at all, but a consequence of how the universe stores information? Our observable universe has a boundary. A cosmic horizon defined by the maximum distance light has been able to travel since the Big Bang. Just like the event horizon of a black hole, this cosmological horizon has a finite surface area. Some models now propose that the total information content of everything within our observable universe is encoded on this two-dimensional surface. The acceleration of the cosmos, the very effect we attribute to dark energy, could simply be a result of this fundamental information limit. Think of the universe as a computer with a finite hard drive. The amount of information that can be stored on the cosmic horizon is not infinite. As the universe expands, this horizon grows and its surface area increases, allowing for more information to be stored. The energy associated with this process of allocating new information, this cosmic memory upgrade, could be what we perceive as the repulsive force of dark energy. It is not a ghostly energy field pushing galaxies apart, but a side effect of the universe managing its own data. This reframes our entire cosmic history. The evolution from a hot, dense fireball to a vast, structured cosmos of galaxies is not just a story of matter and energy cooling down. It is a computation, a colossal processing of information unfolding according to its initial programming. The geometry of spacetime, the distribution of galaxies, and the ultimate fate of everything are all emergent features of this cosmic calculation. This information-based perspective stands in stark contrast to traditional cosmological models that treat the universe as a collection of substances like matter, radiation, and dark energy. evolving on a pre-existing stage. Here, the stage itself is built from the computation. While still a developing theory, this view provides a potential pathway to solving the dark energy puzzle without inventing new physics. It suggests the answer was not hidden in some unknown particle, but in the fundamental nature of reality itself, written in the language of information on the boundary of everything we can ever see. This holographic view of reality, for all its elegance, creates a devastating new puzzle at the very edge of a black hole. It is called the Firewall Paradox, and it presents an astronaut with a horrifying choice. According to Einstein's general relativity, an astronaut crossing the event horizon should feel nothing special at all. The horizon is not a physical wall. It is a point of no return, a one-way street in the geometry of space. The astronaut should pass through it smoothly, unaware of their impending doom as they are stretched and pulled towards the singularity. Yet, the holographic principle, combined with the sacred rule that information cannot be destroyed, seems to demand something very different. To preserve information as the black hole evaporates, the quantum fields at the event horizon must be intensely entangled with the radiation leaking out, the Hawking radiation. But there is another quantum requirement. For the astronaut to have a smooth, uneventful passage, the quantum fields they encounter just outside the horizon must also be deeply entangled with the fields just inside the horizon. The paradox is this: a single quantum unit cannot be maximally entangled with two different things at the same time. It is an impossible love triangle for information. So, one of these entanglements must break. Physicists realize that to save the information from being lost, the entanglement across the horizon must sever. And the moment that connection snaps, it would release a cataclysmic amount of energy, transforming the event horizon from a silent gateway into a blazing wall of fire, an incandescent barrier of high-energy particles that would instantly vaporize any astronaut. This is the firewall, a concept that pits the smooth spacetime of general relativity directly against the information-preserving demands of quantum mechanics. You either have a peaceful fall and lose information violating quantum law, or you preserve information and get burned to a crisp, violating Einstein's principle of a smooth horizon. This paradox is not a flaw in the holographic principle, but a sign that it is pointing us toward an even deeper truth. The very existence of the firewall suggests that our concept of a continuous, reliable spacetime completely breaks down at the horizon. It forces us to consider that spacetime is not just emergent, but profoundly unstable or discontinuous in such extreme environments. Perhaps an astronaut never actually encounters a defined event horizon at all. Maybe the locality of events, the idea of here versus there, simply melts away, meaning the astronaut is destroyed not by a wall of fire, but by the dissolution of the spatial stage itself. Resolving this conundrum may require us to see spacetime as even more fluid and illusory than we currently dare to imagine, a temporary pattern that can literally tear apart under the weight of its own contradictions. These cosmic paradoxes and puzzles all point toward a single, profound need, a theory that can seamlessly unite the quantum world with gravity. String theory has long been a leading candidate for this ultimate unification, and it provides a remarkably elegant home for the holographic principle. At its heart, string theory replaces the idea of point-like particles with unimaginably tiny, vibrating loops of energy. The different vibrational patterns of these strings give rise to all the fundamental particles and forces we observe, from electrons to photons. But this beautiful idea comes with a staggering requirement. The universe must have more than the 3 spatial dimensions we experience. For the math of string theory to work, it needs a total of 10 or 11 dimensions. We do not perceive these extra dimensions because they are curled up into a space so fantastically small that they are hidden from our view. Within this framework, a powerful concept emerges, the idea of a brane. Short for membrane, a brane can be thought of as a multidimensional object existing within the higher dimensional space of the universe, often called the bulk. Our entire cosmos, with its 3 dimensions of space and 1 of time, could be one such brane, a vast, floating sheet adrift in a higher dimensional reality. This is where the holographic principle finds a powerful new voice. The holographic duality, the idea that a gravity-filled universe can be described by a quantum theory on its boundary, can be perfectly interpreted as a relationship between physics on a brane and physics in the bulk. The 3-dimensional world with gravity that we seem to inhabit could be the interior of a specific kind of brane. Meanwhile, the 2-dimensional quantum theory that encodes it, the one without gravity, lives on the boundary of that brane. This framework transforms string theory from a purely abstract theory of everything into an indispensable laboratory for testing holographic reality. Physicists can now use this brane world picture to build precise models. They can take a quantum field theory, which we understand very well, and define it on the boundary of a brane. Using the rules of the holographic correspondence, they can then deduce exactly what the universe with gravity must look like in the bulk. It is like having a complete instruction manual for building a world. You start with the known quantum instructions on the flat surface, and the theory tells you the precise geometry, the specific particles, and even the behavior of black holes that must emerge in the higher dimensional space. This tool allows researchers to probe the deepest mysteries of quantum gravity from a safe distance, using the well-mapped territory of quantum physics to explore the wild, uncharted frontiers where space and time break down. String theory, with its branes and extra dimensions, provides the fundamental scaffolding, the architectural plans, for how a holographic reality could actually be constructed from its most basic vibrating constituents. This cosmic computer did not spring from modern physics alone. Its philosophical roots reach back decades to the brilliant and unconventional mind of John Archibald Wheeler. He was a physicist who helped shape our understanding of nuclear fission and gravitation, yet his most enduring legacy might be a simple 3-word phrase, it from bit. Wheeler proposed a staggering idea that every particle, every force field, every facet of reality ultimately derives its existence from information. He envisioned a universe built not of substance but of billions upon billions of binary answers to yes or no questions. Is a particle here or there? Is its spin up or down? At the most fundamental level, the universe is not playing with marbles, it is flipping cosmic coins. Each flip, each bit of information, is what actually manifests as the physical world we perceive. The holographic principle is the direct, breathtaking descendant of this philosophy. It takes Wheeler's it from bit and gives it a physical address, a location. All those bits, all that foundational information, is not floating in the volume of space. It is painted on the cosmic boundary. Our 3-dimensional reality is the result of that information being processed, the ultimate output of a cosmic calculation. This forces a radical shift in perspective. We are trained to see the universe as a collection of things, stars, planets, atoms. But the information-theoretic view asks us to see it as a vast, dynamic network of relationships. What is an electron? It is not a tiny ball. It is a node in this network, defined entirely by its relationships and interactions with everything else, all encoded as information. In this picture, the laws of physics we have painstakingly discovered are not arbitrary rules written on a cosmic wall. They are the algorithms, the unbreakable software code that governs how this cosmic information is processed and transformed. Gravity, electromagnetism, even the flow of time itself, could be emergent properties of this universal computation. This perspective blurs a line we once thought was absolute, the line between the physical and the computational. Are we living in a universe or inside a computer of unimaginable complexity? The question is no longer purely philosophical. It pushes us to ask what or who is running the program. Is the cosmos a self-computing system, an autopoietic entity that generates its own reality through the act of processing information about itself? The answers remain hidden in the quantum static at the edge of our understanding, but the path to finding them is now clear. We must learn to read the code. For all its elegance, the holographic principle faces fierce opposition from a significant part of the physics community. The most substantial criticism targets its mathematical home, the ADS/CFT correspondence. Skeptics argue this is a perfect solution for a universe that is not our own. The correspondence works with mathematical precision in an anti-de Sitter space, a cosmos with a geometry that curves inward. Our observable universe, however, is best described by a different model called de Sitter space, which is expanding at an accelerating rate due to dark energy. This is not a minor detail, it is a fundamental difference in the very shape of reality. Critics contend that applying the holographic principle to our cosmos is like using the blueprint for a submarine to build an airplane. The core principles might share some logic, but the final product is utterly different. Without a proven mathematical dictionary for our own de Sitter universe, the holographic principle remains a magnificent idea trapped in the wrong reality. Beyond the mathematical mismatch lies the stubborn issue of proof. Despite the heroic efforts of instruments like the holometer, no one has yet detected the definitive signature of holographic noise. The signal remains hidden, lost in the quantum fuzziness we can already measure. For many, this lack of direct, irrefutable evidence keeps the principle in the realm of compelling philosophy rather than established physical law. It is a theory that explains so much on paper, yet refuses to leave a clear fingerprint in our experiments. Then there is the profound challenge of interpretation. What does it actually mean for our daily lives if the universe is a hologram? If our senses are merely decoding a projection from a distant screen, is the tree falling in the forest still real if no one is there to project it? The principle seems to flirt with a kind of cosmic solipsism, where the solidity of the world is an illusion. This can feel less like a scientific theory and more like a metaphysical stance, raising questions that physics alone may never be able to answer. These criticisms are not meant to destroy the idea, but to temper excitement with rigor. They remind us that the journey to validate a new paradigm of reality is a marathon, not a sprint, filled with wrong turns and dead ends. The true strength of the holographic principle may lie in its ability to withstand this very scrutiny, forcing its proponents to refine their models and search ever more creatively for the evidence that could one day turn a stunning speculation into a fundamental truth of our cosmos. This holographic view of reality forces a profound question about the very nature of our own minds. If the solid world is a projection, then what is consciousness? The materialist perspective, which holds that mind is purely a product of the physical brain, begins to tremble. Your brain, with its neurons and synapses, would itself be part of the projected illusion, a complex image within the hologram. So how could a phantom brain generate real, subjective experience? This suggests that consciousness might not be a mere byproduct of matter, but something more fundamental, perhaps a feature of the cosmic computation itself. The world you perceive, then, is not the ultimate reality, but a magnificent user interface. Think of the screen on your computer. You do not interact directly with the machine's raw code with its ones and zeros. You interact with icons, windows, and cursors, a simplified representation designed for you to navigate and understand. Our three-dimensional reality, with its solid objects and reliable laws of physics, could be exactly that, a brilliantly designed interface that allows our conscious awareness to interact with the underlying, incomprehensible data stream of the cosmos. This is an idea that has haunted philosophy for millennia. It echoes Plato's allegory of the cave, where prisoners mistake the shadows on the wall for reality, never glimpsing the true forms casting those shadows. It resonates with Immanuel Kant's distinction between the phenomena, the world as it appears to our senses, and the noumena, the world as it truly is in itself, forever beyond our direct perception. The holographic principle gives these ancient thoughts a startling, scientific vocabulary. Our senses are not giving us a direct line to truth. They are filtering and translating an incomprehensible reality into a form we can navigate and survive within. This understanding shatters our most basic assumptions about identity and free will. If the you that makes decisions is part of the projected interface, then how free are your choices? Are they genuine creations of a sovereign self, or are they the predetermined output of a calculation happening on the cosmic boundary? The very continuity of your personal identity, the feeling of being the same person from one moment to the next, could be an emergent property of the information processing, a stable pattern in the data stream rather than a solid, enduring soul. This is not a call for despair, but an invitation to a grander dialogue. The holographic principle builds a bridge between the hard data of physics and the deep questions of philosophy, forcing a collaboration to understand the ultimate nature of existence. It suggests that the search for meaning is not separate from the search for physical laws. They are two sides of the same cosmic coin, two different ways of reading the same magnificent, hidden code. The holographic principle does more than just reshape reality. It offers a master key to the greatest puzzle in modern physics. For over a century, the quest for a theory of quantum gravity has been the ultimate goal, a way to unite Einstein's majestic picture of spacetime with the bizarre rules of the quantum world. These two pillars of physics are brilliant in their own domains, but when forced together, their mathematical languages break down into nonsensical infinities. The holographic principle cuts this Gordian knot with a stunningly simple proposition. Perhaps we have been trying to unify the wrong things. Instead of forcing gravity into the quantum mold, the principle suggests gravity is not a fundamental force to be quantized at all. It is an emergent phenomenon, a collective behavior that arises from a deeper, more fundamental quantum system that knows nothing of gravity. Think of a whirlpool in a stream. The whirlpool is a real, dynamic structure with its own behavior, but you will not find it listed as a fundamental force in the physics of water. It emerges from the countless interactions of water molecules flowing together. In the same way, gravity and the very geometry of spacetime could emerge from the complex interactions of quantum bits on the cosmic boundary. This reframes the entire problem of quantum gravity. The challenge is no longer to quantize the fabric of spacetime, but to understand the properties of the quantum system that gives rise to it. What kind of quantum theory, living on a lower dimensional surface, produces a universe with gravity as one of its emergent features? This is the power of the holographic dictionary. It allows physicists to take a well-understood quantum system and deduce the precise nature of the spacetime that must emerge from it. This approach sidesteps the mathematical nightmares that have stalled other theories for decades. By starting with a quantum system without gravity, researchers avoid the infinite results and contradictions that appear when they try to apply quantum rules directly to the smooth, continuous spacetime of general relativity. The key ingredient in this miraculous emergence appears to be quantum entanglement. The dense, intricate web of entanglement between the boundaries' quantum bits is what weaves the fabric of spacetime in the bulk. More entanglement creates more connectivity, which projects as a stronger, more defined geometric structure. In this view, gravity is not a force that pulls objects together, but a manifestation of the universe's underlying information architecture and the relentless drive of its quantum components to remain entangled. This provides a breathtakingly fresh perspective on the most stubborn problem in all of theoretical physics. The solution to quantum gravity may not be found by looking deeper into space, but by understanding the source code on the boundary from which space itself is rendered. This cosmic code rewrites our very origin story, starting with the Big Bang itself. For decades, the prevailing image has been of a singular point of infinite density, a moment where all the laws of physics break down and our understanding simply ends. It is the ultimate cosmic dead end, but through the lens of the holographic principle, this baffling singularity may simply vanish. What if the Big Bang was not a violent explosion in a pre-existing void, but the moment a cosmic projector was switched on? In this view, the entire history of our four-dimensional universe, from that first searing moment to the galaxies we see today, is a grand projection from a two-dimensional boundary. The initial state of the cosmos was not a point of infinite heat and density in space. It was a specific, finite configuration of information written on that primordial surface. The event we call the Big Bang is simply the first frame of the cosmic movie, the moment this information began to process and evolve. This elegantly sidesteps the singularity problem. The equations of general relativity blow up into infinities at time zero, suggesting a physical impossibility. But on the two-dimensional boundary, where gravity does not exist, the description of that same moment remains perfectly smooth and finite. The singularity is not a real place, it is an artifact of our perspective, a shadow on the wall of the cave that seems impossibly dense from our limited, three-dimensional viewpoint. The subsequent period of inflation, that faster-than-light expansion of spacetime, takes on a new meaning as well. It is not space itself stretching, but the cosmic code executing its initial instructions, rapidly generating the complex data that would project the vast, structured universe we see today. The distribution of galaxies across the sky is not a random scattering. It is the visible echo of that initial information processing, a frozen image of the quantum fluctuations on the boundary at the dawn of time. This reframes our entire cosmic history from a creation of substance to an unfolding of information. We are not the aftermath of a colossal explosion. We are part of an ongoing narrative being read from a cosmic script written at the beginning of everything. The search for the first cause of the universe shifts from a quest for a primal particle to an investigation of a primordial command, the first line of code that started it all. This computational view transforms the cosmos into the ultimate quantum processor. The two-dimensional boundary is not a passive screen. It is the universe's central processing unit, running an unimaginably complex quantum code. The quantum fields living on this boundary represent the active software, a seething, probabilistic program where countless calculations are performed simultaneously. Our familiar four-dimensional spacetime, with its galaxies and gravitational wells, is not the computer itself. It is the stunning visual output, the high-definition display generated by that relentless processing. The laws of physics we have discovered, like gravity and electromagnetism, are not the fundamental rules of the system. They are the user-friendly interface, the stable and predictable operating system that emerges from the chaotic quantum computations underneath. Think of a modern video game. The world you explore on your screen appears as a continuous, three-dimensional landscape with its own consistent physics. But this entire reality is generated by lines of code running on your device's hardware. The code itself is a separate, simpler reality of ones and zeros, of logical operations and memory calls. You never see the code, you only experience the rich world it projects. In the same way, we never perceive the frantic quantum calculations on the cosmic boundary. We only experience their magnificent output as the universe around us. This metaphor helps unravel a profound mystery. How can a seemingly simple, two-dimensional theory produce the breathtaking complexity of our world? The answer lies in the sheer scale of the computation. The boundary contains an astronomical number of quantum bits, and their interactions represent a computational process of almost infinite complexity. From this chaotic, probabilistic soup, stable, classical patterns inevitably emerge, much like the average temperature of a gas emerges from the frantic, unpredictable motion of trillions of individual molecules. We do not perceive each quantum calculation, just as you do not feel each air molecule hitting your skin. We perceive the collective result, the smooth and reliable force of gravity, the predictable orbit of a planet. This is not necessarily saying the universe is a computer built by some advanced intelligence, but that the language of information processing provides a shockingly accurate vocabulary for describing cosmic dynamics. The universe behaves as if it is computing itself into existence, with the boundary theory as the algorithm and spacetime as the real-time render. This perspective does not diminish the wonder of reality. It reframes it, suggesting that the true nature of the cosmos is not substance, but a dynamic, ongoing computation of breathtaking elegance and power. This scale invariance is the boundary's secret weapon. A conformal field theory is not just any quantum system, it is one that possesses a perfect self-similarity. Imagine a fractal pattern like a snowflake or a fern, where zooming in reveals the same intricate structure repeating at smaller and smaller scales. The quantum fields that make up a CFT behave in this same way. The rules governing their interactions do not change, whether you are observing them from up close or from a great distance. This profound symmetry means the theory has no built-in ruler, no preferred scale. It is a universe of pure relationship without any fundamental units of length or distance. And it is from this featureless, scale-less sea of quantum information that the rich geometry of a spacetime with gravity can miraculously crystallize. The collective hum of this vast network, with its countless quantum elements entangled and interacting, does not produce random noise. Instead, it organizes itself into stable, persistent patterns. These patterns are what we perceive as dimensions, forces, and particles in the higher dimensional universe. Think of it like a massive crowd at a stadium performing a wave. No single person is the wave. The wave is an emergent phenomenon born from the coordinated actions of thousands of individuals following a simple set of rules. In the holographic universe, the CFT provides the rules, and the intricate dance of its quantum components creates the spectacular wave of spacetime itself. Mastering the language of these boundary theories is therefore the ultimate act of cosmic translation. Physicists are not just solving equations on a flat surface, they are learning to read the architectural plans for reality. By studying the specific symmetries and correlations within a CFT, they can deduce the precise curvature of the emergent space, the kinds of black holes that can form within it, and even the spectrum of particles that will appear to its inhabitants. It is a dictionary that translates the flat, gravity-less world of quantum physics into the curved, dynamic universe of general relativity. This turns our traditional approach to physics completely inside out. For centuries, we have started with the world we see and tried to deduce its underlying rules. The holographic principle suggests the true path to understanding the cosmos is to start with the fundamental rules on the boundary and watch the universe we know emerge from them. The solidity of our world, the force of gravity, the very passage of time, all might be a grand and inevitable consequence of a deeper, simpler, and utterly alien reality written in the language of conformal symmetry. So how does a dimension simply appear from nothing? The answer lies not in creating new substance, but in reorganizing information. Imagine a powerful novel, its entire story contained within the two-dimensional arrangement of ink on paper. As you read, your mind does not merely see words, it constructs a rich, three-dimensional world. You envision the towering castle on the hill, you feel the vastness of the desert, you trace the intricate corridors of a spaceship. This entire immersive reality, with its depth and geometry, emerges solely from the relationships between the symbols on the page. The words themselves have no height, width, or depth, yet they conspire to generate a universe that possesses all three. This is the essence of emergent spacetime. The quantum fields on the cosmic boundary are like that text. They exist on a flat, two-dimensional surface. There is no up or down in this fundamental reality, no distance or volume in the way we experience it. Instead, there are only relationships, a vast network of quantum connections, and most importantly, quantum entanglement. It is the strength and the pattern of this entanglement that literally builds the geometry we perceive. Physicists have a specific measure for this called entanglement entropy. In simple terms, it quantifies how deeply interconnected two regions of the quantum system are. The astonishing discovery is that this abstract measure of quantum connection translates directly into a geometric distance in the emergent world. If 2 points on the boundary are highly entangled, their entanglement entropy is low, meaning they are deeply linked. In the projected three-dimensional space, these 2 points will appear to be very close to each other. Conversely, if the entanglement between two boundary regions is weak, the entanglement entropy is high, and in our world, those 2 points will be far apart. The distance between stars and the emptiness of the void are not fundamental properties of space. They are a direct readout of the underlying quantum relationships. Dimension itself is a similar illusion. We perceive 3 spatial dimensions because the pattern of entanglement on the boundary is structured in a way that projects this specific depth. The dimension of height does not exist on the flat boundary. It is a collective behavior, an organizational property that arises from the complex web of quantum data. This means geometry itself is not a fundamental stage. It is a derived property, a consequence of how the cosmic information is woven together. The force of gravity is not a fundamental tug between masses, but the experience of sliding down a slope generated by the varying density of entanglement across the boundary. This is a revolution that inverts our entire understanding of reality. We are not living in a container of space. We are living inside a pattern of relationships, a cosmic story whose words are written in quantum code, projecting the magnificent and solid illusion we call the universe. This intricate web of entanglement finds a stunning visual representation in the language of tensor networks. Think of a vast, sprawling city at night, seen from high above. Each light in that city is a single tensor, a mathematical object that holds a piece of the quantum information. The roads and power lines connecting those lights represent the entanglement, the quantum links between them. A simple, grid-like network where each light is only connected to its immediate neighbors would project a flat, uncurved space like an endless prairie. But if you reconfigure the network, making the connections denser in some areas and sparser in others, the projected space begins to curve. a region where the lights are intensely interconnected, with countless roads converging, might project as a deep gravitational well, the heart of a black hole. The geometry of the entire cosmos could be literally drawn by the pattern of these quantum connections. This is not just an analogy, it is a mathematical reality. Physicists can start with a specific arrangement of tensors on a flat boundary, representing a particular quantum state. By following the rules of how these tensors are linked, they can construct a geometric structure that bulges outwards, creating an entirely new dimension. Within this emergent bulk space, they can then derive the behavior of gravity, finding that it obeys equations that are eerily similar to Einstein's general relativity. The force that binds planets to stars and shapes the cosmos is not a fundamental ingredient, but a statistical echo of the underlying quantum data processing. Tensor networks make the magic of holography tangible. They show us that space is not an empty stage, but a living, dynamic tapestry being woven in real time by the ceaseless interactions of quantum information. Every star, every galaxy, and the very vacuum between them is a grand and beautiful pattern emerging from a deeper, simpler reality of pure connection. These holographic models are now painting a radically different picture of the universe's infancy. Some theories propose that the very first moment was not a point of infinite density, but a seething, high-energy state perfectly described by a conformal field theory living on a de Sitter boundary. In this view, the newborn cosmos was fundamentally two-dimensional, a flat and frantic quantum computation. There was no Big Bang singularity, only this intensely active boundary. As this primordial system cooled and lost energy, it underwent a dramatic phase transition, much like steam condensing into water. This shift in the quantum information on the boundary is what we perceive as the emergence of our familiar three-dimensional spacetime. The entire universe we inhabit literally crystallized from that flat, holographic surface. This holographic cosmology directly challenges the standard story of cosmic inflation. In the traditional model, a brief period of hyper-expansion stretched space itself to explain the universe's large-scale smoothness. The holographic alternative suggests this smoothness was not imprinted by stretching, but was baked in from the beginning by the specific properties of the boundary quantum fields. The two models can make subtly different predictions about the oldest light we can see, the cosmic microwave background radiation. This afterglow of the Big Bang is a fossil imprint on the sky, and its faint temperature variations are a cosmic treasure map. Standard inflation predicts a very specific pattern for these variations. Holographic models, deriving everything from the quantum fluctuations on the two-dimensional boundary, can predict a different statistical fingerprint. The differences are incredibly subtle, buried in the way the variations are correlated across vast distances on the sky. Future observatories, like the next generation of space telescopes and ultra-sensitive ground-based arrays, will map this fossil light with unprecedented precision. They will be searching for that telltale signature, a statistical anomaly that betrays the universe's two-dimensional origins. Finding it would be like discovering the pixel grid on the screen of reality, confirming that our cosmic history was not written in the volume of space, but on its ultimate boundary. The very story of our creation would have to be rewritten, not as an explosion in a void, but as a magnificent rendering from a cosmic code. Our most intimate experience of reality is the relentless flow of time. Yet this very flow may be the grandest illusion of all. In the fundamental description of the holographic boundary, the timeless world of the quantum fields, there is no past, present, or future. The entire cosmic history might be written there all at once, a static and complete tapestry of information. The arrow of time we feel so intensely, the irreversible march from past to future, could be something that only emerges when this timeless data is projected into our three-dimensional world. Think of a movie on a DVD. The entire film exists on the disc simultaneously, every frame stored next to the others. There is no flow, no progression on the disc itself. It is only when the movie is played, when the information is processed sequentially by the laser and projected onto the screen, that we experience a story unfolding from beginning to end. Our universe could be working in a similar way. The boundary holds the complete script, but the act of projecting it creates the experience of a flowing present moment. So what powers this cosmic projector? The answer appears to be entropy, the same measure of disorder that Jacob Bekenstein first linked to a black hole's surface. In our world, entropy always increases, creating a clear direction from order to disorder. This is the thermodynamic arrow of time. A cup shatters on the floor, but the pieces never spontaneously reassemble. This irreversible increase in disorder gives time its direction. In the holographic view, this increasing entropy is not a fundamental law of the boundary, but a consequence of how we, as complex structures within the projection, process the information flowing from it. We are like characters inside the movie, only able to perceive the frames in one direction, always moving toward higher entropy, because that is the only way our internal, emergent physics can make sense of the data stream. Our very consciousness, our memory, depends on this irreversible processing. You remember the past because it is a state of lower entropy that has been recorded in your brain structure. You cannot remember the future because it represents a state of higher entropy that has not yet been processed. This suggests a staggering possibility. The feeling that time is passing, the urgency of the present moment, may not be a feature of the fundamental cosmos. It is a side effect of our particular viewpoint from within the hologram, a necessary artifact of how a timeless code is translated into a dynamic, living experience. If you could step outside the projection and view the boundary directly, you might see all of history laid out at once, with the Big Bang and the end of the universe existing simultaneously, eternally connected in a single, magnificent, and silent equation. This relentless drive toward disorder may be the true source of gravity itself. Physicist Eric Verland has proposed a theory so radical it reinterprets one of the universe's most familiar forces. He suggests that gravity is not fundamental. It is an entropic force, a side effect of the cosmos's innate tendency to maximize its entropy, its disorder. To understand this, picture the holographic boundary as a screen made of countless, vibrating bits of information. This screen has a certain entropy associated with it. Now, when a piece of matter, like a planet or a star, approaches this screen, its presence disturbs those microscopic information bits. It effectively displaces them, changing the entropy of that region. The system, striving to return to a state of maximum entropy, pushes back against this disturbance. That push, that restorative tendency, is what we feel as the force of gravity. A powerful analogy is a single strand of DNA floating in water. Left alone, the DNA molecule will curl up into a messy, random ball. This is its high entropy state. If you try to carefully stretch it out into a straight, ordered line, you have to pull against it. The molecule itself seems to resist, not with a fundamental force, but with an entropic one. It wants to return to its messy, high-entropy ball, and that desire manifests as a physical pull. In the same way, matter distorts the informational fabric of space, and gravity is the universe's way of pulling back toward disorder. The most astonishing part of Verland's work is that this abstract concept can be used to derive Sir Isaac Newton's famous law of universal gravitation purely from thermodynamic principles. The familiar equation that the gravitational force weakens with the square of the distance emerges naturally from considering how entropy changes on the holographic screen. This framework does not just reproduce old laws, it makes new predictions. It offers a potential explanation for the mystery of dark matter. What if the strange rotational speeds of galaxies, which we currently attribute to the gravitational pull of invisible matter, are actually a signal? They could be a sign that our standard understanding of gravity as a fundamental force breaks down on cosmic scales. In Verlin's Emergent Gravity, the way gravity manifests from the information structure of space could naturally account for those extra rotational forces without needing to invoke any mysterious, unseen particles. The extra pull we measure might simply be a mismatch, a gap between how we think gravity works and how it truly emerges from the universe's underlying data. This reframes our entire search for dark matter. We may not be hunting for a ghostly substance, but for the subtle signature of reality's holographic code. This brings us to a profound puzzle at the heart of the quantum world, the role of the observer. In traditional quantum mechanics, a particle exists in a blurry cloud of possibilities, a superposition of states until it is measured. The simple act of observation, it seems, forces this cloud to collapse into a single, definite reality. An electron is both here and there until you look, at which point it must choose. This has always been deeply mysterious. Why should conscious awareness have such a privileged, almost magical power over the physical world? The holographic principle offers a radically different, and perhaps more sensible, interpretation. In this framework, the wave function collapse is not a magical event triggered by a conscious mind. It is an update to the cosmic data stream. When a quantum system interacts with a measuring device, and ultimately with the environment, that interaction is a physical process that processes information. This new information propagates through the network and is reflected on the boundary, updating the code that defines reality. The observer, whether it is a person, a camera, or a Geiger counter, is not an external spectator looking in. It is an integral part of the holographic system itself, a complex node within the vast computational network. You are not a ghost looking at a machine. You are a sophisticated pattern of information within the machine, interacting with other patterns. Your act of measurement is simply one part of the cosmic computation influencing another. This provides a much more coherent picture of how the definite, classical world we experience emerges from the fuzzy quantum substrate. It is not that a conscious mind magically crystallizes reality. Instead, the classical world is the stable, large-scale pattern that consistently emerges from the countless interactions and decoherence events within the underlying quantum network. The solidity of a chair is not an illusion that vanishes when you stop looking. It is a robust, persistent data structure maintained by the continuous processing of information on the boundary. This holographic view elegantly sidesteps the strange dualism of the traditional interpretation, where a separate, classical realm of observers acts upon a quantum realm. There is only one system, one unified holographic reality, where everything from a single photon to a human brain is part of the same informational tapestry, constantly evolving and self-consistently defining what is real. The universe does not need an outside observer because it is observing itself through us. This cosmic information limit might actually be the engine behind the universe's accelerating expansion. One of the most elegant applications of the holographic principle is a concept known as the holographic dark energy model. It tackles the greatest puzzle in modern cosmology, the mysterious force we call dark energy, by reimagining its very nature. Instead of an unknown energy field permeating the void, dark energy could be a direct consequence of how much information the cosmos can hold. The model proposes a specific cosmic scale, the future event horizon of the universe. This is not a boundary in space, but a boundary in time, the maximum distance that any future observer will ever be able to see as the expansion of the universe carries galaxies away from us forever. The size of this future horizon acts as the fundamental cutoff, the cosmic data limit. The energy density of the vacuum, the very energy that drives cosmic acceleration, is then tied to this horizon's area. A larger horizon means a lower energy density, and a smaller horizon means a higher one. This is a profound departure from the standard model of cosmology, which inserts a fixed value known as the cosmological constant, an arbitrary number that must be fine-tuned with impossible precision to match what we observe. The holographic model, by contrast, derives the accelerating force naturally from the geometry of spacetime and its intrinsic information capacity. As the universe expands, the future horizon changes size, and with it, the energy density of the vacuum evolves dynamically. This provides a potential explanation for why the acceleration began when it did in cosmic history, and how it might change in the eons to come. The fate of the cosmos, its ultimate expansion into cold emptiness or perhaps something else, is no longer a question of a mysterious substance, but a direct outcome of the universe's fundamental holographic architecture. The force reshaping the cosmos on the grandest scale may simply be the universe managing its own information budget, a breathtakingly simple solution written in the geometry of its final frontier. The structure of a hologram bears a striking resemblance to the intricate beauty of a fractal. Both are systems of profound information efficiency, where the whole is somehow captured within its parts. A fractal, like a fern leaf or a jagged coastline, reveals the same complex pattern no matter how far you zoom in or out. Each tiny segment is a miniature copy of the entire structure, containing the blueprint for the whole. In a similar way, a fragment of a holographic film plate, even a small shattered piece, can still be used to reconstruct the entire three-dimensional image it encodes, albeit with a loss of resolution. The entire scene is not stored in one specific location. It is smeared non-locally across the entire surface, with every region contributing to the whole. This is the essence of the holographic universe. It suggests that any finite region of the cosmic boundary, any single patch of that two-dimensional screen, contains the entangled information necessary to describe the entirety of the three-dimensional cosmos it projects. The entire universe is implicit in every part of its boundary. This paints a picture of reality that is fundamentally holistic and deeply interconnected. The vast, swirling architecture of a galaxy and the frantic dance of a subatomic particle are not separate phenomena. They are two different expressions of the same underlying informational pattern, viewed at different scales of the cosmic projection. The microcosm truly reflects the macrocosm, not as a philosophical metaphor, but as a direct physical consequence of how information is woven into the fabric of existence. We are not just in the universe, in a very real sense, is imprinted within the fabric of every single point. The silent hum of holographic noise may soon be heard by a new generation of ears listening to the cosmos. While the holometer pushed the limits of terrestrial technology, the future of this search is moving into space itself. The Laser Interferometer Space Antenna, or LISA, is a planned gravitational wave observatory that will float in a vast triangular formation with arms millions of kilometers long. This colossal scale will allow it to detect the faintest ripples in spacetime from merging supermassive black holes and the earliest moments of the universe. Crucially, it will also be sensitive enough to listen for the subtle, underlying static that could be the signature of a pixelated reality. If spacetime has a fundamental grain, it should impose a faint, high-frequency noise on every gravitational wave that passes through it, a digital whisper superimposed on the cosmic signal. A pristine, quiet environment in space, free from the seismic rumble of Earth, gives it a chance to hear this whisper for the very first time. Meanwhile, our view of the infant universe is about to become sharper than ever. Next-generation satellites designed to map the cosmic microwave background will analyze this ancient light with microscopic precision. They will be searching for a specific statistical fingerprint in the temperature variations, a subtle pattern of correlations that defies the predictions of standard inflationary cosmology. Holographic models, which derive the entire universe from a two-dimensional quantum system, predict a unique signature in this fossil light. It would be a telltale sign that the smooth, uniform cosmos we see was not stamped by inflating space, but projected from a quantum boundary, its initial quantum fluctuations frozen into the sky. Finding this anomaly would be like discovering the grain of the film on which the cosmic movie was first recorded. Perhaps most astonishingly, we may not need to look to the depths of space at all. The principles of holography could be tested on a laboratory bench. Physicists are now using intricate arrays of ultra-cold atoms, trapped by lasers and chilled to near absolute zero, to create synthetic quantum worlds. These systems can be engineered to behave exactly like the quantum field theories described by the holographic dictionary. By meticulously studying the interactions of these atoms, researchers can watch for the emergence of gravitational phenomena from a system that knows nothing of gravity. They could, in effect, create a miniature holographic universe in a vacuum chamber, observing first and how a collective dance of quantum bits gives rise to the geometry of a spacetime. The coming decades will be defined by this convergence of scales, from the astronomical to the microscopic, all probing the same fundamental question. The data flowing from these experiments will provide a concrete answer, moving a breathtaking philosophical idea into the hard, testable realm of physical law, and finally revealing whether our reality is a magnificent, solid truth or the most profound illusion of all. This cosmic information budget imposes a profound limit on knowledge itself. There is only so much data that can fit inside any given region of space, a ceiling defined not by volume, but by the area of its surface. This is the Bekenstein bound, the ultimate data cap for any piece of the universe. Think of a room you are trying to fill with books. In the old way of thinking, a bigger room could always hold more bookshelves and therefore more information. But the holographic principle tells us that is an illusion. The true limit is not the room's cubic volume, but the square footage of its walls. You could not cram an infinite number of books into any room, no matter how large, because the walls themselves can only hold a finite amount of information. This principle humbles our entire scientific quest. For centuries, we have operated under the assumption that reality is infinitely divisible and knowable, that by looking closer and closer with more powerful tools, we could uncover endless layers of detail. The holographic universe says no. There is a fundamental resolution to reality, a point beyond which more magnification reveals not finer detail, but only a grainy digital static. The universe has a maximum pixel density. This reshapes the very goal of physics. The ultimate theory of everything may not be a set of infinitely complex equations describing an endless reality. Instead, it might be a much simpler set of rules governing how a finite amount of information is arranged and processed on the cosmic boundary. Our most successful theories today, like quantum mechanics and general relativity, are likely just incredibly accurate approximations of this deeper, finite code, effective descriptions that work perfectly within the limits of our cosmic data plan. The search for knowledge becomes not a journey toward an infinite horizon, but a mapping of a vast yet ultimately bounded island of information. We are not discovering pre-etched laws on a cosmic tablet. We are reverse engineering the source code of a simulation, a code that is elegant, powerful, but ultimately finite. The universe is not an open book with infinite pages. It is a magnificent library with a fixed, if astronomically large, number of volumes. Our task is to read them all. This grand synthesis weaves a new cosmic narrative from the most perplexing clues. It begins with the strange thermodynamics of black holes, where entropy scales with surface area, not volume. It finds its mathematical soul in the ADS/CFT Correspondence, a precise dictionary linking a warped universe with gravity to a flat quantum world without it. It draws power from the realization that spacetime and gravity are not fundamental, but emerge from a deeper quantum reality, with entanglement acting as the cosmic thread that stitches the geometry of the universe together. The holographic principle binds these once disparate ideas into a single, breathtakingly coherent story. Our universe is a vast, dynamic hologram. The rich three-dimensional reality we inhabit, with its swirling galaxies and beating hearts, is a magnificent illusion. It is a projected image generated by the relentless processing of quantum information on a distant, two-dimensional screen at the edge of everything. In this radical vision, the bedrock of classical physics crumbles. Gravity is not a fundamental force, but an entropic pushback. Time is not a flowing river, but a projected sequence. Even the particles that constitute matter are secondary phenomena, transient patterns in the underlying data stream. This represents one of the most profound shifts in our conception of existence, a true paradigm change that unifies the domain of galaxies with the realm of quanta under a single, elegant umbrella, the physics of information. It challenges us to accept that the solid stage upon which we live our lives is a grand and beautiful deception, and it dares us to continue exploring this breathtaking possibility, to one day read the hidden code of the cosmos itself. Our journey began at the edge of a black hole and has brought us to the precipice of a new reality. We traced the path from a baffling calculation about entropy to a radical vision of the cosmos as a grand hologram, a magnificent projection from a hidden, two-dimensional surface. This single idea has the power to resolve the deepest paradoxes of physics, offering a pathway to unify quantum mechanics and gravity by suggesting that neither space nor time are what they seem. It forces us to confront the possibility that matter itself is a secondary phenomenon, an emergent pattern in a cosmic sea of information. Though the final, irrefutable proof still dances just beyond our experimental grasp, the holographic principle stands as a towering achievement of human imagination, a testament to our unyielding desire to read the hidden code of existence. The most profound secrets of the universe are not always locked away in distant galaxies. They are often hiding in the empty space between the stars, woven into the very geometry of the void. If this vision of a holographic cosmos has reshaped your perception of reality, we would love to hear your reflections in the comments. For more journeys to the furthest frontiers of knowledge, subscribe to the channel. And always remember to look up at the night sky with wonder, for the ultimate answers may be inscribed in a dimension we are only just beginning to see.